Hello and welcome everybody. This is Basit Qureshi. Today I'm going to be presenting our work titled APEnergy Application Profile Based Energy Efficient Framework for SaaS Clouds. So first we're going to talk about the motivation for this work. Our work takes motivation from the topic of energy efficient data centers. We're going to present APEnergy framework, which is composed of three major components, which are application profiles. We're going to talk about the system model that we've developed for this framework, and we're going to talk about the scheduling algorithms that we're using. Next, we're going to validate our work and conduct some simulation studies to evaluate the performance of the proposed model. Finally, we're going to talk about the conclusions of this work. Better Cloud estimates that by 2020, 73% of organizations around the world would be hosting their services in the SaaS model public clouds. So a solution is to have hyperscale data centers. In 2018, there were about 392 to 400 hyperscale data centers existing worldwide. The benefits of having a hyperscale data center is efficiency in terms of the hardware and the infrastructure controlled by the company. They provide their own custom-built servers. The entire data center is designed to reduce the cooling costs, which is a major issue in power consumption of the data centers. And furthermore, these large-scale data centers are operational 24/7. All major service providers have hyperscale data centers. So here, according to Synergy Research Group, published a report in April 2018. This is the distribution of different hyperscale data centers around the world. Now, not all small and medium scale enterprises can migrate to SaaS and public clouds. There could be many reasons for that. A very common reason is the security, trust, and privacy issues of the data to be put on public clouds. It is also possible data could be of sensitive nature for national and regional concerns. Sometimes it can also be very costly for some workflows to execute in the public cloud. So some challenges to small, medium-scale data centers include infrastructure security, management and maintenance, scalability of the services, new workflow deployment challenges. There could also be issues with failure and long recovery periods, and overcapacity and power outages. Data centers are power hungry, so they create environmental issues, and this has been a huge concern. A major concern is the cost of power and the inefficiency of data center resource utilization. In this work, we focus on small to medium scale data centers. Some major characteristics that differentiate this kind of data center from others are as follows. Low variability in workflows. Typically, a small organization tends to execute similar kinds of applications in their workflows. It is possible to predict the size and resource requirements for an application. For example, each day at 12 a.m., a backup service would be initiated with X number of terabytes of data transfer requested. So due to this low variability and high certainty in application workloads, almost certainly a near constant number of virtual machines are initiated. So based on these characteristics, we study the energy utilization parameters for specific application workflows. We analyze the resources requested by an application workflow, the availability of resources, power consumption requirements. We can efficiently place workflows in the data center, focusing by reducing the overall power consumption of the data center. So to this end, APEnergy, an application profile-based energy efficient framework, is presented. The framework builds application profiles for workflows executed in data centers and records all relevant information in these profiles. Information in the application profile is later used to efficiently place VMs in the data center hardware, improving the overall energy efficiency in the data centers. We validate our work by comparing the framework against two popular workflow schedulers. So very quickly, let's talk about the scheduling problem. In a typical workflow scheduler, as a new workflow arrives at the data center, a scheduler determines the tasks to be executed based on various parameters. In a workflow, tasks from various applications may have to be executed in a certain order. The scheduler may assign one or various tasks to a virtual machine so as to optimize execution times. Usually, a hypervisor would later initialize the virtual machines and assign them to various physical nodes in the data center. So the goal is to minimize execution time for the workflows. Various factors determine an optimal task assignment, which is a challenging problem. Popular schedulers do not guarantee power efficiency. On the contrary, early completion time results in increased power consumption in data centers. So in the proposed APEnergy framework, we extend the existing scheduling paradigm by incorporating energy requirements in task scheduling. The APEnergy framework leverages the availability of an application's data, including expected runtime, power requirements, the frequency of multi-tenancy of VMs per PM, resource allocation to VMs, etc. All of this is done to build profile data structures. Before the initiation and deployment of an application on the cluster, the information available in the application profiles is used by scheduler to optimally schedule the task placement by considering the expected runtimes and power consumption parameters. So the APEnergy scheduler is based on the popular stochastic heterogeneous earliest finish time, which is known as HEFT, HEFT. So in this work, we define two data structures, AP, which is an application profile, and a VM profile, a virtual machine profile. An AP data structure consists of data including workflow ID. Each workflow would be given a unique identifier. Task ID. Each workflow may have many tasks. Each task is given a unique identifier. The arrival time for each task in the workflow. Completion times of a task. Maximum CPU and memory requirements. Power consumed. At the completion of a task, the framework records these information in the AP for future use. A VM profile consists of a physical machine ID. Each VM is assigned a unique identifier, CPU resource requested by the VM, memory requested, and power attributes, including the maximum power utilized. In this work, we assume that power is directly correlated to the CPU utilization. The profiles are periodically updated to maintain the ever-changing energy efficiency requirement in the clusters. We define VM profile and AP as data structures within the framework to support power-aware workflow scheduling in data centers. So this figure gives an overview of the APEnergy framework. As a workflow arrives with multiple tasks, the scheduler controller communicates with the workflow analyzer and resource manager to determine the number of tasks, type of tasks, resources required by each task. All of this is done by asking for this information from or within the AP and the VM profiles. If an AP exists for a task, the status information is pulled from the underlying data structures based on workflow parameters. Resources requested, including CPU, memory, etc., are determined. Information related to task initialization, such as task arrival time, workload, expected completion time, and power consumption are analyzed. Once the cost analysis is completed, the task is assigned to a VM and the VM profile is updated. As the task executes, runtime status parameters such as completion rate, power consumption, starting time, completion time, etc. are recorded in the AP. In case when an AP for a task does not exist, the scheduler estimates the runtime based on workflow using general distribution. We assume that over a period of time with large data availability, the cost analysis normalizes the overall efficiency of the framework. Here we present some definitions given in this work. We assume that each workflow, W of k, consists of a list of tasks, T of k of I, with arrival times, expected completion times, and a power profile is determined from a vector containing the power consumption levels. So PT k of I would be the power intervals at different levels or at different times during the execution of this task. Tasks defined in a workflow are assigned to a set of VMs such that only one task is executed per virtual machine. VMs can be gained and released by any task in a workflow. Each VM has a price associated with it, which indicates the cost to execute a task on this VM for a time frame delta t. Delta t is given by T of EKI, which is expected time, minus TAK, which is the arrival time. The variable M reflects mapping between tasks and virtual machines. As a task complete, the real starting times given by ST of KIX and the finishing times given by FTKIX on a virtual machine VX become available. The completion times can be given by this equation 2, where Tm of Kix is the time to place a task in the VM. The actual finishing time of all tasks in a workflow can be given by equation 3, where we maximize the actual completion times of all the tasks in the workflow W of k. Assuming that there are D number of physical machines, D is a vector which contains all the physical machines within a data center. So we define this variable n, which reflects the mapping of tasks Tk of I in a virtual machine V of x to a physical machine D of y. The primary optimization objectives are to, number one, minimize the cost price of executing the task in the workflow. Number two, maximize the utilization of physical machine D of I by placing the optimal number of virtual machines determined by the AP of the tasks. So we give equation 4, where V of t denotes the total number of virtual machines employed to complete workflow W of k. Price for this particular virtual machine represents the price associated, and delta tki denotes the time to complete this particular task. The optimal placement of VMs per PM is governed by minimization of power consumption costs of a virtual machine. So we give the average of executing a VM with the mapping M on the server dy as price, M, and Y. This is given in equation 5, where P, the variable P, is the power consumption level at a certain time interval, and the price is always between 0 and 1. To obtain an optimal mapping N, we need to maximize the placement of R number of VMs on a physical machine Y such that the relationship is given in equation 6, where we maximize the price for all possible mappings for the tasks on a physical machine Y. We define the maximum CPU utilization theta Y, which is going to work as a threshold on a physical machine, where the value of the threshold could be between 0 and 1. Now we present two algorithms. The first algorithm is the arrival of a new workflow. We consider two criterion for ranking the task. The first criterion is earliest finish time of a task. The second one is lowest price of task available in the scheduling queue. The proposed scheduling algorithm continually creates and updates new and existing mappings of the tasks, VMs, and PMs based on the profiles. It analyzes every task considering its expected completion time and price which is available in the AP. The task list queue is updated with all tasks processed in a workflow and is passed on to the scheduler. The scheduler is given an algorithm too, using a power-aware scheduling algorithm. This determines the optimal cost of efficiently executing the workflow with minimal power requirements by producing a mapping. The VM's tasks and PM's map M of K is initialized for workflow W of K. For each task processed by the controller, the task's times and prices are available in the task list. The scheduler computes the price of assigning a task to a VM based on availability of the VMs. Once a mapping is produced, the tasks are removed from the task list. Based on the frequency of multi-tenancy on a PM and the load factor, the scheduler determines the minimal price of executing VMs on a particular PM using equations 5 and 6, which were shown in the previous slide, whereas we consider the limits of theta of y. If a PM satisfies the criterion is valid, the VM is assigned to this PM and the task is initiated. Alternatively, the next PM satisfying the criterion is sought from the pool of available physical machines. So that was our model. Now we're going to talk about simulation parameters. In this paper, we conduct extensive simulation studies. We compared the proposed algorithm with two scheduling algorithms. The first one is a stochastic heterogeneous earliest finish time, simply known as HEFT, and the robust time cost algorithm. Both of these are scheduling algorithms which have been quite extensively used in recent research works. For simulation, we use a tool called CloudSim framework. We modify that and we extend it to simulate a cloud computing cluster environment. We assume a data center with 5 different types of virtual machines, given as T2 Micro, T2 Medium. These are similar to the Amazon AWS EC2 instance types. We assume that the number of VMs for each type is infinite. The VM instances can be acquired at any time. 2 workflow templates are created for evaluation. These workflows are based on real-world application workflows. These are taken from the Pegasus workflow repository. We're looking at epigenomics, which is gene sequencing workflow, and the broadband workflow, which stores data for earthquake signs. The time between 2 workflows is a variable given by Poisson distribution with initially no profiles. Initially, when no profiles are available. For experimental evaluation, we assume that the VM boot time is 2 seconds. We consider 2 different test setups, test setup 1 and 2. Test setup 1 is used to verify the feasibility and task completion efficiency for the 3 scheduling algorithms. We define 4 different scenarios with different sizes of the scenarios in terms of number of virtual machines and number of workflows to be executed. So for scenario 1, the virtual machines setting is 200 with workflows 200. Scenario 4 with 800 virtual machines and 2000 workflows. So we categorize scenario 1 and 2 as lightweight workflows, scenarios 3 and 4 as medium scale workloads. Test setup 2 is used to compare the energy efficiency of the proposed algorithm against the HEFT and the RTC. So we define 5 scenarios in setup 2. Scenarios 5 and 6 are considered as small to medium weighted workflows. Scenarios 7, 8, and 9 are large and very large workflows for this environment. The difference between setup 1 and 2 is in test setup 1, we're using 100 physical machines in the data center and 100 physical machines for test setup 2. We conduct two sets of experiments. So first we look at the CPU utilization and task placement efficiency of the proposed APEnergy scheduler, and we compared the results with RTC and HEFT. So in order to determine the efficient utilization of resources such as CPU for physical machines, we consider the task placement efficiency of the proposed scheduler. This can be determined by analyzing the ratio of CPU resource requested by a virtual machine versus the actual utilization of CPU at a physical machine, which can be given in equation number 7. We observe a high variance in average CPU utilization efficiency of the APEnergy scheduler when compared to HEFT and RTC in scenario 1. However, as the ratio of the number of applications and VMs increases per physical machine, the efficiency also increases. So due to a low number of VMs per PM, the APEnergy scheduler increases the ratio of the number of VMs per PMs. This reflects an increased number of physical machines with near zero workloads. Consequently, the average CPU utilization efficiency for scenario 1 is lower for APEnergy scheduler in comparison with HEFT and RTC. Now we look at the second aspect of our experimentation, which is the energy efficiency. The objective of this experimentation is to analyze the impact of larger workloads, increased number of virtual NPMs, and the threshold of the energy efficiency on the APEnergy scheduler. In test setup 2, the number of physical machines is increased to 150 with CPU availability threshold increased to theta in the range of 0.35 and 0.85 with the maximum load set to 20. In order to determine the power consumption over a period of time, we calculate the average power consumption for a physical machine given by variable P average in equation 8. We estimate the total energy A consumed by the cluster over a period of H hours in terms of kilowatt hours given in equation 9. Here we assume that the Pmax is 350 watts based on the physical requirements of a server, and minimum P is 150 watts. In scenario 5, with 200 virtual machines and 400 workflows, there are 39 idle physical servers compared to 2 and 8 for HEFT and RTC schedulers respectively. In scenario 5 and 6, where the workload is comparatively less, the APEnergy scheduler is 2% and 14% more efficient than RTC and HEFT schedulers. In the presence of DVS, APEnergy is 19% and 38% more energy efficient than RTC and HEFT. We concurred that the effect of increasing the number of idle machines by efficient placement of virtual machines in the cluster improves the power efficiency of the cluster. In conclusion, we present APEnergy, which is a profile-based energy efficient framework. It makes a good trade-off considering various parameters consisting of the cost of virtual machine placement, power usage, CPU utilization, and PM load factors. The performance of the APEnergy scheduler is compared to RTC and HEFT schedulers extensively through simulation studies. Our results show that the APEnergy scheduler dominates the benchmark schedulers in energy efficiency and exploits the data center resources by increasing the multi-tenancy of virtual machines per physical machine, therefore increasing the number of idle machines in the cluster. And thank you very much.